Hi, everybody. I'm Anna, and I'm going to be presenting on me and Andrew's cellular automaton that we made for assignment 2. Our research question that we're addressing with our CA is how can we model the formation of a river across a landscape composed of patchy wetlands and drylands? The CA that we developed to describe our system is a 3-state system, which you can see on this diagram. Each cell on our 2-dimensional array represents a 50 square meter area on the landscape, and cells can take on one of 3 states: dryland, wetland, or river. And we start by initializing our model using percolation, which randomly assigns dryland and wetland cells and adds them to our array. And then we change one cell in the middle of our array to river cell. And then as time progresses, we can watch how that river spreads across the array. And the main mechanism through which the river spreads in our model is that a wetland cell can turn into a river cell when it has at least one neighbor that is a river cell. And then we also implemented mechanisms through which cells can switch from dryland to wetland and vice versa. So wetland cells turn into dryland cells at a rate proportional to the number of dry cells in its neighborhood, and then also incorporating a drying probability, which gives it a stochastic property. And then on the other hand, dryland cells turn into wetland cells through a similar process that's dependent on the number of wetland cells in its neighborhood and a reigning probability. Now we're going to quick describe some of our detailed methods and their associated assumptions. For our rules, one assumption we made is that we assume that once a cell becomes a river cell, it stays that way, so rivers can't dry up. For our initial conditions, we assume that we start with one river cell, which could represent like a new source of water, such as a spring. And then we use an array that is 100 cells by 100 cells with periodic boundary conditions. Our CA used synchronous updates, where the whole array updates at each time step, depending on the state of the array at the initial time step. And finally, we used a more neighborhood for our array. So cells neighborhood includes the diagonal neighbors, since we thought that was a potential direction that water could flow. Now we're going to show how our CA progresses with the following conditions. Using a more neighborhood, rainfall probability, and drying probability of 0.025, proportion of initial wetland areas of 0.25, and then going for 100 time steps. So here you can see 3 runs of these same conditions, each going for 100 time steps, and you can see the yellow river spreading across our array, each of the runs. Yeah, so this slide shows the outcomes of 8 trial runs of our CA with those same initial conditions and parameters, and how the system looks after 100 time steps. And since our model contains a stochastic component, we get different resulting river shapes each time we run the model, which you can see here. But overall, they all take on similar shapes. And yeah, so this slide shows the outcomes of running the model with different initial proportions of wetland cells in our percolation step. So the model runs that I just presented, we used a proportion of wetland cells of 0.25, so the center panel in the figure. And so we kind of played around with that parameter to see how it would impact things. So after 100 time steps, if the initial proportion of wetlands is 0.1, so the graph on the left, the river sort of stops progressing across the landscape because there's too much dry areas and not enough wetland areas for the river to flow through. But then as we increase the initial proportion of wetlands to 0.25 or to 0.5, then we can see that running our model results in a greater total area of river at the end of our model run. And then this slide shows the outcomes of running our model with different rainfall and drying probabilities, so rprob and dprob. As you can see, as these probabilities increase, the system becomes more stochastic, basically as the drylands and wetlands can switch back and forth between states more frequently, which allows the river to spread much wider. So on the way right, you can see like if the probability of switching between dry and wet states is too high, it kind of breaks our model. And if it's too low, there's not enough change to allow the river to find its way between the wet patches and the river can't spread. And then, yeah, we also played around with increasing either RProb or DProb to make them not equal each other. And we found that whichever one is greater than the other, if we change it, that state, whether dry or wet, it will overtake the other in the system. So yeah, one of the main takeaways from our model is that you need a high enough proportion of wetland areas for a river to be able to spread across the landscape. We also found that rainfall and drying can't be too sporadic, such that the river cannot connect wetland areas. And they also need to counteract each other equally to avoid wetlands or drylands taking over the landscape. And finally, we thought about some future improvements we can make to our model, which could include incorporating landscape topography. So high elevation and low elevation areas impacting the flow of water across the landscape could be something we could add. We also could allow the rivers to dry up, which is something that we didn't allow in our model. And finally, we could add in human influences to the system, such as damming the river. Thanks for listening.